Okay. Good morning to all. So now we know that in this class, uh, so the ILO is internal flow. So here the main concept is we are going to study about the internal flow. So until now we studied about the external flow in forced convection. Okay. Now we are going to study about the internal flow. Okay. So in this again we have to use some empirical correlations. So in internal flow, mainly we have horizontal pipe flow and annulus flow. Horizontal pipe. Suppose if the flow is taking place through the horizontal pipe. Okay. Similarly through the annulus. So I already explained that what is meant by annulus, and we saw some of the annulus diagrams. Okay. Now the first of all we are going to study about the internal flow. What is meant by internal flow? So in the case of internal flow, let us take horizontal pipe. Okay. Suppose if you consider the horizontal pipe, and now how the boundary layer is formed, layer is formed, and how the velocity profiles are taking place. Similarly, how the thermal boundary layers are taking place, we will see. Okay. So in internal flow, the boundary layer is the boundary layer means it may be either hydrodynamic boundary layer or thermal boundary layer. Both are taking place similar to the external flow. Both are taking place similar to the external flow. So we know the concept of boundary layer. What is meant by boundary layer and how the boundary layer is framed and all those things. Okay. So now we will go to study about how the boundary layers are formed in the case of internal flows. That means in the case of horizontal pipe flows, either it may be laminar flow or turbulent flow, how it will take place. Okay. So if you see this diagram, so here we are considering a horizontal pipe. Here we are considering a horizontal pipe. Okay. So which is having some diameter. Okay. Through the horizontal pipe, we are flowing some fluid with some velocity, let us say that is u infinity or u, whatever it may be. Okay, so to study the boundary layer concept, and velocity distribution, so here we are concentration on the velocity profiles. That means how the velocity takes place in the case of a pipe. In the case of a pipe, how the velocity profile takes place. Okay, so that is also called as development of laminar velocity profile in the pipeline. Laminar velocity profile. That means in the case of laminar flow, how the velocity profile changes in a pipeline. We are saying. Okay. So now let us consider a pipeline which is having diameter D, which is having diameter capital D. So here it is mentioned capital D. Okay. And we know that radius equal to D by 2. We know that radius equal to D by 2. And we are taking the fluid which is flowing with velocity. Fluid, it may be either air, water, oil, whatever it may be. Okay, we are considering the fluid which is flowing with some velocity u infinity. Okay, now to study the velocity profile and to study the thermal boundary layer, we are considering three sections of the pipeline. We are considering three sections. Let us say the sections are A, this is the section of A, this is the section of B, and this is the section of C. Okay, so we are considering the pipeline. Okay, now we know that in the case of pipeline. So if you see the this is the boundary layer. This is the boundary layer. If you see here, the dotted lines represents the boundary layer. Okay. So where in the case of plates, we have only one boundary layer like this. Okay. Whereas in this pipeline, we have boundary layer like this. Why? Because in the case of flat plates, or in the case of external flow, the flow is exposed to the air. That means we have the free stream. Okay. Whereas in the case of pipeline, it is the confined space. We have the confined space. That means the velocity profile or the boundary layer which is taking place only through the pipeline. That means inside the pipeline. Whereas there it is taking place outside the plates. Okay. So that's why here we are having the boundary layer. So which is shown in the dotted lines. Okay. So now we know that at the surface of the pipeline, Okay, that means at the wall of the pipeline, we have zero velocity. We have zero velocity that is represented here. So here we have zero velocity. That means at both sides of the pipe, we have zero velocity. Okay, so now with the in increase in x direction, that means with increase in length of the pipe, what happens? So the velocity so if you see here, this is the velocity. If you consider only the half of the above section of the pipeline, let us say, because this is the symmetric in x direction. So if you consider one section, if you analyze one section, then the other section also follows the same one. Okay, so if you see the above axis, so that means this is the pipeline. We know that here it is zero velocity because of the viscosity effect, and that is called as, also already I explained it, that is called as no viscosity effect. Because of the no viscosity effect, here we have zero velocity. Okay, and in this radial direction, that means in y direction, let us say, that is in y direction, or that is also called as the radial direction. Okay. In this direction, so from the pipeline, that means from this wall to in this direction, the velocity increases because of the viscosity effect reduces. So that the velocity develops. That means the velocity increases. If you see here, if you see here, here this is the velocity. So here we have zero velocity, and here this is the velocity. If you coming downwards, this is the velocity. If you come downwards, then this becomes the velocity. That means if you see this, the velocity increases. Similarly, if you consider the bottom portion also, here we have zero velocity. So here we have some velocity. Here we have some other velocity, and here we have some other velocity. If you see this in this direction, the velocity increases from 0 to here. And similarly, in this direction, again, the velocity increases from 0 to here. Okay, so this is the velocity profile at A section. Okay, so similarly, if you consider at the B section, okay, then what happens? At the walls, we have zero velocity only, that does not change. Okay, but if you see the shape of the velocity profile, if you see the shape of the velocity profile at this section, here we have, this is the shape, and if you consider this B, the shape changes from this shape, this to in this way. Okay, so that means at the radius of the pipeline, the velocity further increases. If you see the radius, if you see the velocity on axis for both these velocity profiles, so this is, let us say, this is u1, and let us say this is u2. If you see these two diagrams, u2 is greater than u1. u2 is greater than u1. Okay, and so the dashed lines represents the boundary layer. The dashed line represents the boundary layer, and these represents the velocity profile. Okay, so further increase in x direction, we are considering the C section. So at the C section, at the boundary layers, at the pipeline, at the wall of the pipe, we have zero velocity, and with the increase in this direction or in this direction, the velocity increases. So here this is the velocity, here this is the velocity, and at the axis this is the velocity. Similarly, here also this is velocity, this is the velocity, and this is the velocity. So that means the velocity further increases. So if you see this, if you compare the velocities for these three figures at the axis, so here let us say this is u1, u2, and u3. So u1 is lesser than u2, again u2 is also lesser than u3. That means u1, u3 is greater than u1 and u2. That means at the axis, on the axis, we have the maximum velocity because of the no slip condition, and on the axis, that means at the center of the pipeline, we don't have any viscosity effect. Okay, so this is the final velocity profile, and this is the developing velocity profile. These two are called as that means this one and this one, these two are called as developing velocity profiles, and this is called as developed velocity profile. That means after this, we don't have any change in the velocity profile. Okay, so that means, and The C position is the position at which this boundary layer meets the axis line. The velocity profile C, that means the developed velocity profile starts at the point where we have the boundary layers. This is the boundary layer and this is the boundary. These two boundary layers, that means these two dashed lines meet at one point. Okay, so let us say here, that point, at that point only the developed velocity profile starts. The developed velocity profile starts, and after that, if you go in this direction in pipeline, if you go in this pipeline, that means if L increases, then we don't have any boundary layer effect. That means up to here only we have the boundary layer effect because the flow increases. The flow increases. Okay, so up to the point where the boundary layer ends or the developed velocity profile develops is known as the hydrodynamic entry length. Hydrodynamic entry length. That means that is the length of the boundary layer formation of the pipeline. Okay, so at which the boundary layer ends. That is called as hydrodynamic entry length. So after that, I already told you that this is the developed region. This is the developed region. In this direction, we have the developed region. Okay, so that is called as hydrodynamically developed region. That means after that, we cannot find any formation of boundary layers. We cannot find any formation of the boundary layer. Okay, so this is about the development of laminar velocity profile in the pipeline. So that means internal flow. Okay. Similarly, if you see the turbulent boundary layer, we know that in the case of turbulent boundary layer, the velocity increases because of the increase in velocity are taking place. We don't have any smooth curve formation. This is the turbulent velocity profile. So if you see this velocity profile and this velocity profile, so here we have the smooth edge. Here in the laminar flow, we have the smooth edge. Whereas in the case of here, we can find similar somewhat blunt edge. This is called as blunt edge. So this is the turbulent core. This is known as turbulent core, and this is called as turbulent velocity profile. So that is the difference. Okay, so in the case of velocity profile, if that belongs to laminar velocity profile, so we can find the smooth or sharp edge at the end of the velocity profile on the axis. Okay, whereas in the case of turbulent flow, we cannot find that because of the changes in velocity, the random changes in velocity, we cannot find any smooth formation. That's why we have the blunt edge formation. This is called as blunt edge. This is called as blunt edge. That means in the case of turbulent flow, this velocity profile is called as turbulent velocity profile, and we cannot get any particular shape. Okay, but here it follows the parabolic shape. This shape is called as parabolic velocity profile. But here we can't say any shape of the profile. Okay, the velocity profile changes according to the velocity. Okay, so again we know that in the case of turbulent region we have the laminar sublayer also. This is the laminar sublayer. This is the laminar sublayer. Whereas in the case of flat plates we have laminar sublayer on one side. Okay, since here we have two walls. Let us say if you assume these two walls as two flat plates. If you assume these two walls as two plates, then we have two laminar sublayers. This is laminar sublayer and this is also laminar sublayer. Okay, so this is about the hydrodynamic boundary layer formation. So similar to this, we have the thermal boundary layer. Again, in thermal boundary layer, we have two types. In the case of plates, we saw that if the plate is heated, that means if the fluid which is having, if the cold fluid flows over the hot plate. Similarly, if the hot fluid flows over the cold plate. Okay. So we saw that similar to here also we have development of thermal boundary layer in a cold pipe. That means the pipe is having less temperature over the fluid temperature. That means the hot fluid is flowing through the cold pipe. Hot fluid is flowing through the cold pipe. Okay. So this is the thermal boundary layer formation, and these are the temperature profiles. So if you see the temperature profile at the edge, that means at the wall or on the wall, we have the low temperature as compared to the temperature in between the pipe. That means at the center of the pipe, we have maximum temperature as well as maximum velocity. Okay. So why we have maximum temperature at the center of the pipeline? Because the hot fluid is flowing. The hot fluid is flowing. That's why at the center we have the maximum temperature, and at the walls we have the minimum temperature. Why? Because we are using the cold pipe. Suppose if we have hot pipe through which cold fluid is flowing, through which cold fluid is flowing. Okay, so this is the diagram. So that means cold fluid, hot pipe, hot because of the hot pipe, we have the maximum temperature at the nearer the walls. If you see the temperature near the wall, here we have maximum temperature. Similarly, at the bottom side also we have the maximum temperature, and at the center we have the minimum temperature because the pipe is having high temperature as compared to the temperature of the fluid which is flowing through the pipeline. Okay, so this is the shape. This is the shape of the thermal boundary layer in a heated pipe. That means in a heated pipe means through which the cold fluid is flowing. Through which the cold fluid is flowing. Okay. Similar to here, the hot fluid is flowing over through the cold pipe. Okay. So these are the thermal boundary layer, development of thermal boundary layer and development of velocity profiles. These are the development of velocity profiles, these two, and these two are the development of the thermal boundary layer. Okay. So here also we have thermal entry region similar to here, hydrodynamic entry length. Here also we have thermal entry region. Okay. After that, thermally developed region, hydrodynamically developed region. Hydrodynamically developed region, that means there is no change in boundary layer over this portion. Okay, that means already developed. So this is developing stage and this is developed stage. Okay, so this is about the formation of velocity boundary layer and thermal boundary layer in internal flow. In internal flow. So we already studied about the external flow, and similarly that here we have the internal flow. Okay. So is it clear? Or anybody have doubt? Respond in the chat box. Both are similar. Yes, both are similar, but there we are considering the velocity, whereas here we are considering the temperature. We are considering the temperature. Okay. So in the case of laminar flow, in the case of hydrodynamic boundary layer, we are considering the velocity distribution, whereas in the case of thermal boundary layer, we are concentrated on the temperature distribution. That is only the difference. Okay, so you can explain this in a way that if you consider these two as two flat plates, this is one flat plate. If you consider the pipeline, so for the pipeline we have two walls, bottom wall and upper wall. So if you consider those two as the plates, you can explain the similar way. Okay, so that is the difference. That is the difference. Okay, respond in the chat box if anybody is having doubt. If anybody is having doubt, respond in the chat box. Regular 28, Gautam. Regular 28, Gautam. Regular number 28. Okay, so is it clear? Is it clear? The formation of thermal boundary layer and velocity boundary layer in internal flows. Okay. Now we will go to solve some problems based upon these internal flows as well as the external flows. Okay. So we already saw some these formulas for the internal flow also. Fluid is flowing inside the tube or through the annulus. We already discussed these formulas, and I also show you in the data book also. Okay. So if the tube is having Reynolds number less than 2300, the flow is called as laminar flow in the case of internal flow. Internal flow. Okay. If it is greater than 2300, the flow can be said as turbulent flow. Okay. So generally we follow the formula. Nusselt number equal to 0.023 RED to the power 0.8 into PR to the power N. So this is called as famous equation, that is Dittus-Boelter equation. Okay. Where N is used as 0.3 for cooling process and it is 0.4 for heating process. If we use it if we use the application of heating process, then n we can take as 0.4. Otherwise, if it is for cooling process, we have to consider that as 0.3. Okay. So in some of the problems, this formula is also given in some other way. In some other way, where this formula is also given. Suppose if the formula is given, let us say if that formula is instead of 0.023, if in that formula if you have 0.03, okay, then you have to use that formula only. Don't use this formula. If the formula is mentioned in the problem, then you have to use that formula only. Okay. So these are the annulus. We know that these are the annulus. Okay, this is the annulus which is having circular cross section. Here we have rectangular. Here we have outer side we have rectangular, and inner we have the circular section. So these are called as annulus. Now we will solve some problems. I take down this problem. Water at 20 degrees centigrade flows through a small tube. That means internal flow, because the water is flowing through the tube. That's why this belongs to internal flow. This belongs to internal flow. Okay. 1 mm in diameter. Diameter is given at a uniform speed of 0.2 meter per second. That means velocity of the water is given. Inlet temperature of water is given. Diameter of the tube is given. The flow is fully developed. That means what is meant by fully developed flow? I already told you that. So if you see this thermal boundary layer, over this region is called as developed region. That means fully developed region. This is called as a developing region. Okay. So over this region, I already told you that there is no formation of boundary layer. That means we have to consider this one. That is called as fully developed region. That is called as fully developed region. Okay. The flow is fully developed at a point beyond which the constant heat flux of 6000 watt per meter square, so this is meter square, watt per meter square is imposed. Okay, so the heat flux of 6000. Okay, how much farther down the tube will the water reach 74 degrees centigrade as its hottest point? That means inlet temperature is this one. This is outlet temperature. This is heat flux. This is the diameter, and this is the speed of the water. That means velocity of the water which flows. Now what we have to calculate is at what point, at what length of the pipe we get the 74 degrees centigrade. That means we are having we are having so this is the pipeline. Okay, so let us say this is the pipeline. So here we have, at this point we have 20 degrees centigrade, and at this point we have 74 degrees centigrade. Now what we have to do is we have to calculate what is the length. At what length we can get the 74 degrees centigrade temperature. Okay, so for that purpose diameter is given, the velocity speed of the water flow is given. Okay, so when the temperature changes from 28 degrees to 74 degrees centigrade, the heat flux is also given. This heat flux is also given. So we have to calculate only the length of the pipeline. Okay. So, this is the problem. This is the configuration. Okay. So this is the pipeline. This is the pipeline through which water is flowing with velocity 0.2 meter per second. Inlet temperature is 20 degrees centigrade. Outlet temperature is 74 degrees centigrade. Diameter is given. Heat flux over the pipeline is also given. Okay. So now what we have to calculate? We have to calculate N. This value we have to calculate. So water flows through the tube, that means pipeline. Inlet temperature is given, diameter is given, velocity is given, heat flux is given, outlet temperature is given. So now what we have to calculate is we have to find out the distance of tube at which water is heated to a temperature of 74 degrees centigrade. That means at inlet temperature we have 20, outlet 74. Okay, so we have to find out this length. Okay. So we know that the first step is we have to calculate the mean film temperature. That is here the fluid is water. Okay, so mean temperature equal to inlet temperature plus outlet temperature by 2. What is inlet temperature? 20 plus 74 by 2. Okay. So that equal to 47 degrees centigrade. Here the fluid is water. Here the fluid is water. So we have to take the properties of water at 47 degrees centigrade. So where we can get those properties from the data book. We can get those properties from the data book. Okay. So the physical properties of water at this temperature at 47 degrees centigrade from data book. We have to take from the data book. Okay. So I will show. So I will show you, I think, water or water. Okay. This is oil. Okay. So this is for water. This is for water. Okay. So similar to air, we have for the water. These are the property values of liquid at saturated state. This is for water. Okay. So here the temperatures are given 0 degrees centigrade, 20 degrees centigrade, 40, 60, 80. In this way the temperatures are given. But here we require at 47 degrees centigrade. We require at 47 degree centigrade. That means that is in between 40 to 60. That is not 40, that is not 60. But here we have the values at 40 and 60 degrees centigrade. But we require at 47 degrees centigrade. Okay. So I already told you that how to calculate in if the temperature is in between those two values in the previous class. So by following that procedure, you have to calculate at 47 degree centigrade. Okay. So at 40, this is 995. At 60, it is 985. So in between these two values only we have for 47 degrees centigrade. Similarly, we have to calculate for mu, Prandtl number, Cp, and for thermal conductivity. Okay. So from that we calculated. Just 1 minute. Okay. So by taking the values from 50 to 40 degrees centigrade and 60 degrees centigrade, we have to calculate at 47 degrees centigrade, and we got these are the values. Rho equal to this one, Cp, mu, Kf, that means thermal conductivity of fluid, or let us say that is K, and this is Prandtl number. Okay. So after calculating that, we have to calculate the Reynolds. So here, no need to use all those formulas. Why? Because here we are going to calculate the length of the tube only. We are going to calculate the length of the tube. So we have to find out the distance. That means L we have to calculate. Okay. So for that purpose, what we have to do is, we know that mass flow through tubes, mass equal to, this is not P, this is rho. Okay, just wait. This is rho. We know that from continuing the equation. Okay, so mass equal to rho into U into A. Rho is given, U is given. Rho is given in the problem. Density, we know that. Velocity is also given. And area equal to pi by 4 d square. Pi by 4 d square. So we have the rho value, velocity is given, diameter we know that value. So we can calculate this mass. This mass. This is the mass value we got. But we know that the energy which is taking place, Q equal to mCp delta T. Q equal to mCp delta T. Q equal to mCp delta T. But here heat flux is given. So we know that the relation between heat transfer and heat flux is heat transfer equal to heat flux into surface area. Heat transfer equal to heat flux into surface area. Okay. So heat flux into surface area equal to this one. So that means so this is the formula we have to consider. So heat flux into surface area equal to mass into specific heat into delta T. Delta T means outlet temperature minus inlet temperature. Here the surface area, we know that surface area of the pipe equal to pi dl. Surface area of the pipe equal to pi into d into L. So d value is given, that is 0.001 meters. 0.001 meters into L. Okay, substitute this value in this equation. Uh, we have this Q value that is given in the problem, heat flux. So this is AS pi into 0.001 into L. Mass we already calculated here, so we have this value. CP is also took from the data book, and these two values are given in the problem itself. So substituting all those things, only the unknown is this L. So if you substitute all those things and if you calculate it, after simplification, we get L equal to 1.96 meters. Okay, so in this way, we have to calculate the length of the pipeline, length of the tube. Okay. Is it clear? Or anybody is having doubt? Respond in the chat box. Is there any doubt in the way or doubt while solving the problem? Okay, respond in the chat box. Regular number 8, Pawan Kumar. Regular number 8, Pawan Kumar. Regular number 8, Pawan Kumar. Regular 8. $77, Bon Prasad. 77. Roll number 77, Bon Prasad. So we'll go to the next problem. So a refrigerated truck is moving at a speed of 85 km per hour, where ambient temperature is 50 degrees centigrade. So here the speed of the truck is given and the ambient temperature is given. The body of the truck is of a rectangular shape. Rectangular shape of size is given, length 10 meters, width 4 meters, and height 3 meters. Assume the boundary layer is turbulent. So clearly here, this is clearly mentioned. The boundary layer is turbulent. That means we have to consider the turbulent flow. There is no need to calculate again Reynolds number. So to verify for laminar or turbulent. And the wall surface temperature is at 10 degrees centigrade. Okay. Neglect heat transfer from vertical front and back side of truck. So here, suppose if you consider the truck that is given in the rectangular shape, okay, so let us say this is the rectangular shape. Then what happens? He told that neglect heat transfer from vertical front and back sides. That means this is the vertical front. Okay, so this is the vertical. So what he told is neglect heat transfer from vertical front. That means this is the vertical front we can neglect. Similarly, this is the vertical back side. So you can neglect these two. And flow of air is parallel to 10-meter long side. That means air is flowing through the parallel to these two pipes, these two plates. Okay. So that means it is the flow is parallel to 10-meter long side. Okay. So now calculate the heat loss. Calculate the heat loss from the four surfaces. Calculate the heat loss from the four surfaces. For turbulent flow, the formula is given here. So here the formula is given. So by using the, we have to use only this formula to calculate the heat transfer. Okay. So this is the solution. This is the given data. Velocity is given. Fluid atmospheric temperature is given. Length is given. Width, height, surface temperature is given. Okay. So what is area? Area equal to L into W plus H. Okay. So into 2 into 2. Okay. So that is because top surface and bottom surface. So that equal to 140. If you substitute L equal to 10, W equal to 4. So 4 plus 3, 7. 7 into 10, 70. 70 into 2, 140. Okay. So first we have to calculate film temperature, 30 degrees centigrade. Now properties of, what properties we have to consider? Properties of the refrigerated truck is moving at a speed where ambient temperature, that means ambient air. We have to consider the fluid as air. We have to consider the fluid as air. So the properties of air at TF, 30 degrees centigrade, from the data book. So these are the values. Okay. Now we have to calculate the Reynolds number. Okay. We are calculating this Reynolds number not for checking the flow, for the flow. Okay. Why we are calculating is to substitute here. Okay. So even though if you verify, you can verify. So the flow is turbulent since it is greater than 5 into 10 to the power of 5, because we are having the two plates, top plate and bottom plate, and the Reynolds number is greater than 5 into 10 to the power of 5. So it is verified. The flow is turbulent. Okay. Now use that formula that is given in the problem. The formula is given in the problem. So you can use that directly. NU equal to this one. Okay. Now substitute all those values and we know that NU equal to HL by K. So from this we can get H. Okay. Now therefore total heat transfer rate from all the four surfaces, H equal to A into TS minus TS. Okay. All the values are given. H value calculated here. Area is given, we find out here. Okay. And TA minus TA. So substituting all those things and you can get Q equal to 2.6 into 10 to the power of 5 watts. Q equal to 2.6 into 10 to the power of 5 watts. Okay. So this is the value of heat transfer. This is the value of heat transfer. Okay. So I will stop here. Okay. Now I will take the attendance. Okay. So if anybody is having doubt, is it understood? Respond in the chat box. Roll number 8, regular number 8 and 77. Roll number 8 and 77. No response. Okay. Now I will take the attendance. And please respond in the chat box. Those I am calling. Okay. No need to respond to the remaining members. Roll number 1. Roll number 1. 2, 3, 4, 6, 7, 7, 10 to 26. Roll number 10 to 26. Regulars. 10 to 26. And for supply exam, okay. No attendance is given when anybody is going to supply exam. Okay. 10 to 26. Anybody is there? Roll number 10 to 26. Regular 10 to 26. 9 okay. 9 okay. 10 to 26. Right. 29. 29. Regular 29. Okay. 21. Okay. Number 21. Okay. 21. 22. 21 okay, 30 okay, 32 regular, 32 regular, 32 34 35 34 35 regulars, 38 regular, 38 40 regular, 40 41 okay, 46 regular, 46 regular, 46 okay, 43 okay, 48 47 okay, regular, 48 regular, 48 50 regular, 50 51 okay, 51 okay, 52 regular, 52 53 54 55 54 okay, regular, 54 okay, 59 59 regular, 59 regular, 62 to 67 regular, 62 to 67 58 okay, regular, 62 to 67 70 to 74 70 to 74 62 okay, 62 okay, 73 no 60 okay, 81 81 82 okay, 77 okay, 77 okay, 75 okay. Right now you can leave. Then laterals. LE1 27 okay amma, regular 27. LE1 3 LE1 3 LE1 3 6 7 LE3 okay, LE3 okay, 6 7 1856 okay, 12 15 laterals, 12 8 okay, 12 15 11 okay, 16 okay, 17 18 LE LE is 17 18 okay nama okay, 17 18 25 21 okay, 25 24 present okay, 25 27 LE 25 okay, LE 25 okay, 27 LE 27 25 okay amma, 27 30 LE 30 LE 26 okay, LE 30 35 37 26 okay, 35 34 okay, 35 37 36 okay, 39 40 LE 35 okay, LE 35 okay, 38 okay, 40 43 43 LE 43 42 okay, LE 43 48 49 LE 48 49 47 okay, LE 48 49 okay, regular 11 okay, 7 LE 7 okay, LE 48 okay, LE 50 okay, 11 18 53 LE 22 okay nama, LE 45 okay, 5462, 5462, LE35, okay. Okay, okay, LE4, okay. So I will stop here. Okay, thank you. We will meet in the next class. Okay.